Okay. So the last section here is one-to-one functions and inverses. Okay. When we talk about, let's just talk about the word inverse for a moment. If I start with the operation 3 times 2 and I get 6, how do I take 6, or what do I need to do to 6 to get back to the original 3 that I started with? Divide by 2. Gets me back to 3, which is what a value I started with, right? So what do we usually say that multiplication and division, they're inverse operations. They undo each other, right? Okay. So that's really the structure of what we're going to talk about here today with inverses. Okay. So the inverse of a function is a rule that acts on the output of the function and produces the corresponding input. Okay. So this 6 was essentially the output, okay, of multiplication. We enact this, divide by 2, and it gets me back to the corresponding input that I started with. Okay. If we think about graphically with a image like we talked about yesterday with the composite functions, basically what we have is we have a, I'm going to just say f, and then over here I'm going to say f, and I'll put a superscript of a -1. And we'll talk about that notation here in a little bit. But essentially what this means, what this right here means, is that you're going to take your input. You're going to run it through your first function, and it's going to give you an output, right? So I'm going to say that output is y. Okay? You are then going to take that output, and it becomes an input in your second function, which is the inverse of the original. And if they undo each other, what do you think I should get back out of this second function when I'm done? If I took 2 times 3, or 3 times 2, that gave me 6. I divided them by 2, and it got me back to 3, right? So that's what we're doing here. I take x, plug it in, got y. Take y, run that through my function. What do I want it to get you back to? Back to x. Okay? If that happens with 2 functions, those 2 functions are inverses. Okay? Does that make sense, everybody? Now, here's the idea, and this is going to be a key component to this. This was a domain value for f, right? What is it over here for f inverse? Is it the input or is it the output over here? It's the output, so it's a range for f inverse. Okay? This number here is a range value for f. What is it right there for f inverse? It's an input, right? Inputs are domains. Okay, so if 2 things are functions, or 2 functions are inverses, then the domain of one function actually becomes the range of the inverse. The range of one function becomes then the domain of the inverse. Okay? So they switch spots. Domains and ranges switch from a function to its function's inverse. It says the inverse undoes or reverses what the function has done. However, not all functions have inverses. Okay? Those that do are called one-to-one. Okay? So we've got some functions that are one-to-one, some functions that are not. If a function is one-to-one, a function is going to have an inverse. If a function is an inverse, it is also one-to-one. Does that kind of make sense? Okay, that's a definition, so it's a biconditional. Now, what does one-to-one mean? So let's get into that. What's the definition for a function? What does it mean for something to be a function? Okay, so every x value that my function is defined for has one and only one y value, right? So we've talked about this graphically with what test? The vertical line test. The vertical line test is the structure that we use to see if the function fits that definition, or the graph fits that definition of being a function. And basically what it says, if I take for any x value, so let's say this is my curve, for any x value, do I get just one corresponding y value that goes with it? Okay, and the vertical line test will validate that, okay, or confirm that for me. Okay, so that means every x has one y. And think about the reasoning for this. And I think I talked about this in one of the videos. I think we were talking about this when I was gone. But if I have something like this, if I have x equals y squared, it's that graph there. It's still a relation. Okay, but is it a function? No, because if I say everybody look at the y value that goes with 4. Everybody look at the y value that goes with the x of 4. Are some of you looking at a y value of 2? And are some of you looking at a y value of -2? Okay. So that's the problem. That's why we want to have this classification of functions, because we want to be able to everybody be on the same page of knowing, okay, if I input 4 into this rule, I know the one and only one output that I'm going to get. In this case, I would get 2, and that's a problem. So that's why it's not a function. Okay. Is this a function? So now if I say everybody look at the x value of 2 and tell me what is the y value that goes with it, is everybody focused on the same y value? Everybody's focused on 4. Okay? Now here's my question. This is where we get to 1-to-1. If I say everybody look at the y value of 4. Everybody look at the y value of 4. Now tell me the x value that goes with it. You have two choices, right? Some are going to look at positive, some look at negative. That idea violates what 1-to-1 is. Okay? Because we want everybody to be on the same page. I want to say look at the y value, and you tell me exactly the one and only one x value that goes with it. Just like you can do when you have a function. And I asked about the x's and the y's. Okay? So what if I did this? Now if I say everybody look at the x value that goes with the y value of 4, is everybody looking at 2? That's the only x value that goes with the y value of 4, right? So that would be a 1-to-1 function right there. Okay? Because you can do that, I can play that game where everybody look at this x value and tell me the y value that goes with it, and everybody would tell me the same y value. Okay? And then I can reverse it and say, okay, now I'm going to tell you a y value, everybody tell me the x that goes with it, and everybody tells me the same x. Okay? That's the idea of being 1-to-1. So there's a lot of different ways that we structure this or talk about this. And we'll come back and talk about these mappings here in a moment. But the definition of a function to be 1-to-1, okay, it says a function with domain A is called a 1-to-1 function if no two elements of A have the same image. Okay? Now, what does that mean? Well, when I say it has a domain A, well, domain are your inputs, right? So our domain are x values, correct? So when it says if no two elements of A, so no two x values, okay, no two x values have the same image. Okay, well, if we go back to talking about like transformations inside geometry, we talked about images and pre-images, right? Okay. And in this case, the image is referring to the y value that goes with those elements of A. That make sense? Okay. So two elements of A, that means we're talking about two x values. Their images are their y values. So basically what this is saying is that no two x values can have the same y value. And that's exactly what we were having here. And that's why this failed. That's why this image here was not 1-to-1, because two x values, -2 and +2, they had the same y value of 4, right? And that fails the definition of 1-to-1. Okay? Notation-wise, it says f of x sub 1 cannot equal f of x sub 2 whenever x sub 1 does not equal x sub 2. This means your y values need to be different. y1 and y2, they need to be different when x1 and x2 are different. Does that make sense? Okay. An alternative way of saying it is the only time that your y values can be the same, the only time your y values can be the same is when you choose x values that are the same. Otherwise, it's not one-to-one. Does that make sense, everybody? Okay. The way I was introduced to this concept is the phrase, because it parallels well with what we know about a function and how we define it. For a function, we say every x value has one and only one y value, right? Okay. To be one-to-one, we then reverse and say every y value has one and only one x value. Okay? And that's we call that a one-to-one relationship. Okay? Yes? Yes. The top one tells me it's going to be a function, and then that bottom one tells me it's going to be one-to-one. Okay, so the question is, can I look at this and decide this? First thing I want to do is I want to talk about this mapping. Okay, and I think the mappings are sometimes, at least when I was in school, they were frustrating to me, confusing to me. But understand that they are just simply a way of telling you a set of ordered pairs. So when I say 4 arrows to 10, okay, 4 maps to 10, this is my pre-image and this is my image. Okay, if we think about that terminology. But essentially he's giving me the ordered pair 4, 10. This is giving me the ordered pair 3, 7, 2, 4, 1, 2. Does that make sense? And if I asked everybody to look at the y value that goes with 4, is everybody looking at the same y value? If I ask that question with 3, is everybody looking at the same y value? If I ask that with 2, is everybody looking at the same y value? If I ask it with 1, is everybody looking at the same y value? So because of every single x value that I chose, and we all look at the same y value, this thing is a function. Does that make sense? Okay. Now if I did this, I said, maybe I put an arrow like that, and I say, now everybody look at the y value that goes with x is 1. Some of you would be looking at 7, some of you would be looking at 2, right? And that's the problem with functions, or not being a function. That would fail the vertical line test, so that relation would not be a function. So this is a function, okay? So f is a function. Now my question is, everybody look at the x value that goes with that y value of 2. Is everybody looking at the same x value? Everybody's looking at 1, right? What if I say everybody look at the x value that goes with the y value of 4? Is everybody looking at the same x value? Yeah. Is that the same situation if I ask you to look at 7 or 10? Everybody's looking at the same x value, right? So does that tell you every x value had one and only one y value when we look this way? And every y value has one and only one x value when I go that way. Does that make sense? This function is one-to-one. Okay? Now, I'll give you a better way, I think, of analyzing that here in a little bit, or making that decision. Now if I look at this one, okay, if I ask everybody to look at the y value that goes with 4, is everybody looking at 10? What about 3? Is everybody looking at 4? What about 2? Is everybody looking at 4? What about 1? Is everybody looking at 2? So G is a function. Every x value had one and only one y value. Okay, I never asked you to look at 2, and it went to another number other than 4. Okay, so that is a function. Now my question is, if everybody looks at 4 as my y value, tell me the x value that it pairs with. Is there 2 answers for that? 2 choices. So what's that tell me about, even though G is a function, what's it tell me? Not one-to-one. Okay, now, why is this? Well, why is it important for us to tell whether a function is one-to-one or not? Okay, if a function is one-to-one, it is going to have an inverse. It's going to have a rule that undoes it. Okay? So meaning, like, if 4 goes to 10 in that first one, because that first relation is 1 to 1, there should be some rule that takes 10 and puts it back to 4. Make sense? Okay? In that second image, it's not 1 to 1 in G, so there is not an image, there is not a rule that will take 4 to 10 and then take 10 back to 4. Okay? So that's the use for the benefit of knowing whether a function is 1 to 1 or not. It's going to tell us that it has an inverse or not. Okay? So Jimin said something about looking at the horizontal line test. Yes? Okay. So this here says if a horizontal line intersects the graph F at more than one point, then we see from the image that there are numbers x1 and x2 that are different. Okay, so this means x1 and x2 are different. Okay, we would agree that image-wise they're different, right? They're different x values. Okay. However, the y value that pairs with x1, that y value right there, which is f of x sub 1, and this y value right there, which is f of x sub 2, what would you tell me about those y values? How do they relate? They're the same, right? And that's what that red horizontal line tells me. Okay? So what this is saying in this situation is that f of x sub 1 equals f of x sub 2 when x1 does not equal x2. So I'm getting the same y value for different x values. Does that make sense? And that violates the definition of being 1 to 1. Okay? So the horizontal line test is the tool that we're going to use to determine whether we meet the condition of being 1 to 1. Okay? That's what this says down here. It says a function is 1 to 1 if and only if no horizontal line intersects the graph more than once. Okay? What does the graph have to do? What does that blue graph have to do in order to fail the horizontal line test? If I'm reading that graph left to right, it's starting to increase, right? Left to right. What does it have to do to fail? It has to start to decrease then, right? So if you have a function that shows both behaviors of increasing and decreasing, then it's not going to be 1 to 1 because it's going to pass through the same y values at some point or repetitive y values for different x values, and that's a problem. Okay? When we talk about functions that are only increasing or only decreasing, they're referred to as one word monotonic. Okay? Tonic referring to tone. Okay? And in this situation, tone referring to essentially the behavior, increasing or decreasing. Okay? Mono means what? One. Okay? So one behavior. One, whether it just be increasing or just one decreasing feature. Okay? Monotonic functions are going to be 1 to 1. All right, so we got this x to the third. Okay? Now I want to talk about the notation here. And this is essentially the purpose of using that notation, using the f of x. What do they tell me when they use f of x? That thing is it's a function. So it's already past the vertical line test. The author, the reason we use this notation is the author is giving me insight that I wouldn't already have if they would have written this, because those are the same graph, right? Okay? That top one tells me you've already passed the vertical line test. Y equals x to the third tells me you don't know. So you got to check. Does that make sense? Okay? So I already know, based on this notation here, that every x has 1 and only one y. Now I got to check, does every y have 1 and only one x? So the way we do that, take our horizontal line, and it's just like the vertical line test. We're going to pass it through the entire graph and see if there's any situations, any y values, in which we cross our graph twice. And there are none, right? So this thing passed the vertical line test, and it passed the horizontal line test. So this is 1 to 1. So if it's 1 to 1, there should be a function that undoes it. So like right here. Yeah, so that's always increasing there. And even if I go like x to the 5th or x to the 7th or x to the 9th, this starts to get flatter right here, but it's always going to be, for different x values, the y values are going to be incrementally a little bit bigger. So this is still increasing, even though graphically, just because of the way we draw it and how zoomed out we are and that kind of stuff, might look like it's flat and, or horizontal. So that is 1-to-1. So that means there's a function that undoes that. So here's my question. If f of x is equal to x cubed, give me an x value. That's easy to cube. 2. So f of 2 is equal to 8, right? Okay. What function or what rule would allow me to take that 8 and get back to 2? Okay, so if I take the cube root, that would be the rule, right? Okay, so this is how we write this. Okay, you see numerically that those two things, this is my input or my domain, and 8 became my output, right? Or my range, and that was just for f. Now in f inverse, 8 was my input, and 2 was a range value. Does that make sense? Do you see how in f, the input or the domain becomes the range or the output in f inverse? That makes sense? Okay. Now notation-wise, this is the symbol that we use for inverses. Okay. It doesn't have to be f. We can use g, we can use h, we use whatever letter we want. But we use that superscript of a -1. It's a superscript. It's not an exponent. Okay. There's no algebra that you do with that. It's just a symbol. It's a notation that tells you inverse. Does that make sense? Okay. So I just want to make sure that we know that this does not equal 1 over f. Okay? Because that's what a -1 as an exponent means, right? Okay, so that is a label, a name, a structure for us identifying the inverse. Okay? Here's a question. And this, I'll leave this up to you to write down, but it's just the definition of an inverse. Basically, it takes, well, we'll read it. It says 1-to-1 function with domain A and range B. We have domain A and range B. The inverse then, for the function, we label it f with that superscript of -1. Then takes domain B and range A. What does that tell me? What does that tell me right now? It's saying if the, or let's use the same letter. So domain A is a bunch of x values, right? Let's say that every x value is a lowercase letter a, or represented by a lowercase letter a. In the range, capital B, is all my y values. Let's say that is represented by lowercase b's. Does that make sense? So capital A is the set of all of these x values, and capital B is the set of all of these y values. And we're just calling those x and y values A and B respectively. So if A comma B is on f of x, then B comma A. You see how it said it now? The domain is coming from B and the range is coming from A on the inverse. So if A comma B is on f of x, or is on, I'm just going to write on f, then B comma A is on f inverse. Okay, so if I gave you, let's go real quick. See if I have it open here real quick. Yes, Jackson.
Can I go to the bathroom?
Yes. Not right here, though. All right, so question number 10 on that practice test. If I give you f of x, drawn down here, and I ask you graph its inverse, okay? We're going to use that logic that we just talked about, that if a point like negative 3, 2 is on f, and negative 2, 1 is on f, 1, 0, 6, negative 1. If those are all on f, what points, so those are all your a comma b's, right? What is going to be on f inverse? If I look at that point right there, what do I do with that to find the point that's going to be on f inverse? Switch the x and y. So 2, negative 3 would be on f inverse. So then on this test, I'm just going to graph 2, negative 3. What about this one? Flip the x and y's, becomes 1, negative 2, right? So if AB is on f, then BA is on f inverse. So then it could be 0, 1, it'll be negative 1, 6. And that's then how we end up graphing that function, that inverse. Does that make sense? Now, we're not going to have time to, like, if I give you the rule, how to go through it algebraically to come up with the inverse rule, is that what you're saying? That's not going to be on the test. No, we're not going to have time to do that. We will talk about that because it is an important feature, but just in terms of keeping pace and not pushing the test back, we'll talk about that stuff on Monday of next week. Let's see here. Let's look at a graph real quick. Let's go. Something that we're familiar with. That thing right there. Is that a function? What? So that is a function past the vertical line test. Is it 1-to-1? Why? Fails the horizontal line test. Okay, so is it going to have an inverse? No. But wait a minute. That's x squared, right? What have we always talked about as being the thing that undoes x squared? Square root. So isn't the square root the inverse? Okay. What kind of numbers you allowed to take square roots of, though? Only positive numbers or 0, right? Okay. So here's my question. That doesn't have an inverse. This thing does not have an inverse. But does that have an inverse? Is that a function still? Pass the vertical line test. Does it now pass the horizontal line test? Yes, it does. Okay. So now that's 1-to-1, right? So that will have a rule that undoes it. What's the rule? Square root of x. Now I'm going to graph this real quick, just to kind of hopefully prove a point with you. If that's y equals x, that's the line y equals x, which we did talk about this in geometry. Now I go back to geometry quite a bit, and I know that was a year for us, or sorry, more than a year for some of us. But there's a lot of geometric features and facts and relationships that we need to talk about in this class. If I take that line y equals x, okay, and we have talked about the idea that if x squared is going to have an inverse, then this point A right here of 0.72, comma 0.51 is on f, then what should be on the inverse? Yeah, I should be able to flip that, right? Okay, so I'm going to take that point and flip it. And how did I flip that? I reflected it across the line y equals x. If you go back to transformations that we talked about in geometry, chapter 9 geometry, we had a rule that said if we're going to reflect across the line y equals x, if a comma b, okay, then when you reflect across the line y equals x, it becomes b comma a. Is that exactly what we just talked about in regards to the definition of an inverse? Yes. Okay. So reflections across the line y equals x are the rule, or is the rule, graphically, for how we generate an inverse. So what this will do, okay, I should be able to take A and move A, and it will show its reflection, okay, across the line y equals x. So I'm going to take that, and I will let it trace A prime, just show me where it's been. So that should be, that curve right there is the inverse of x squared. And you guys said that that was square root of x. Does that convince you, when I type in square root of x and it graphs the whole thing, that it was indeed the reflection of x squared for when x was bigger than 0? Make sense? Now here's the reason we have to do this, why we have to restrict this domain for x squared. Because if I didn't, okay, so let's say that I didn't want to delete all that. That's stupid. If I take x squared, okay, because we can reflect anything over the line y equals x. Anything we want to reflect across any line, right? So let's say I start with that, and we've already said that this is not one-to-one, but let's say we neglected that. We didn't pay attention to that. And I reflect that across the line y equals x. So I'm going to reflect this across that line, and it gives me that new thing right there. You see the problem now? That new thing is not a what? It's not even a function. Okay? So if our functions are not one-to-one, and we reflect them, it's going to give me a relation that is not even a function in itself. Does that make sense? Okay? So your inverses have to be functions too, or as well. That's why we need to check to see if the horizontal line test is confirmed, because when I reflect across the line y equals x, that horizontal line test actually becomes the vertical line test for this graph. Does that make sense? Okay. Anybody have questions on this? Can we understand the purpose of inverses? Okay, now what's going to happen is throughout this course, and we'll talk more about this on Monday, obviously on the test tomorrow, really the only question I'm going to ask you about inverses is going to be this one. Okay, or something very similar to this. Okay, hopefully you can tell me that main feature about an inverse. Okay. On Monday, we'll talk about how we generate, maybe if I give you like 1 over x, okay, as the function. Can you tell me its inverse algebraically? Can we come up with that process? Okay. We'll do a little bit of that on Monday. Or if I give you two functions, like x squared and radical x, and I ask you, determine if these are inverses without graphing, there's a procedure for that. It's composite functions allow us to do that. So we'll talk about that on Monday. But that's going to be the only question I ask you on the test this week. But, like I was getting to, is the rest of this course, we talk about exponentials. Does anybody know what the exponential inverse is? Not quite. If you're going to talk about logarithms, exponentials and logarithms are inverses. Okay. You guys remember talking about on your calculators, if I type in like sine of 30 degrees, okay, sine of 30 gives me 1/2 back, right? You remember hitting the sine -1 key and typing 0.5 in, and it gives you back the angle of 30? Okay, that's the sine inverse, okay? That's a huge portion of trigonometry, is understand that relationship between the sine function and its inverse function, okay? How 1, I type in the ratio of side, or 1 gives me the ratio of sides, so sine of 30 degrees gives me the ratio of the opposite over hypotenuse to be 1 over 2 all the time, right? If I type in then sine inverse of that ratio, it spits back the angle of 30 degrees. Okay? So that relationship of inverses is going to be persistent pretty much through every topic we talk about throughout the rest of the year. Okay? So that's going to be important. So we'll talk a little bit more about it. And when we get to those sections, we'll talk about this again. But right now, just kind of glaze over the top of it and get the real understanding of the definition, and maybe hit it a little bit harder on Monday. Yes, Jimmy. Number 11. You work for 30 days or 30 hours in a week and earn $450. And the next week you work 40 I should say hours, and earn $530. Express salary. Okay, so one. Hopefully we looked at this and said, well, he knew he meant hours here, so that's typo. Right? Is everybody okay with that? Like, I can't in the next week work 40 weeks. Doesn't make sense. But 30 hours and $450 is my ordered pair, right? Okay. All ordered pairs are going to be a number of hours, comma, an amount of money. The next one is 40, comma, 530, right? Okay. It says a linear function. Well, linear functions are, I'm going to say S of t. Okay, eventually is what they want me to use, but a linear function is this, right? So I need a slope, right? So I need a slope, and I'm going to take 530 minus 450, that gives me 80. And 40 minus 30 gives me 10. So what's that telling me right there? That's my slope. But 530 minus 450 was money, right? 40 minus 30 was hours, right? $8 an hour. It tells me my rate, correct? Okay. Now, you don't know B, so you got a couple different ways of doing this, but I would use this. Right? You guys remember that? And I'm going to go Y minus 450, because that's what Y1. M was 8. X minus X1, which would have been 30. So Y minus 450 equals 8X minus 240. Add 450 to both sides. And I've got my Y, right? Okay. I've just run out of room here. So, whoa. There we go. So if I add 450, what's that give me? 190? 210? So Y equals 8X plus 210, right? So now they want me to write it in terms of S and T. So this was my money. This was my hours, right? So hours is the time. So I'm going to rewrite this as S of T is equal to 8T plus 210. It's just redefining my variables. And now part B says, what do I do for part B then? Plug 24. Okay. And what does that mean then? When I plug 24 and I get a value back, that's how much money I would make working 24 hours. Obviously to run out of time here, but is there anything else that you guys are contemplating on there, struggling with? If you can complete that, feel comfortable with those, you're going to do fine tomorrow. Like I said, bounce ideas off one another. I do not have a key, and I do not anticipate making a key. So use each other, okay? Do some research, do some digging. If something doesn't make sense, ask me questions, email me. So this evening, I'm probably not going to be checking my email. It's just the way my schedule is tonight, okay? I got to take my daughters to dance and stuff like that. So if you do have a question, ask that prior to hopefully 2 o'clock, and I can maybe get back to you as soon as possible with an explanation. Okay. Yes.
Is number 5, is that saying like 4 different things, like graph the active value of x plus 5 and the graph?
No, it's saying so. It only wants you to graph x plus 5, the absolute value, for x values that are less than -1. So basically what you're doing is you're taking your graph at -1. Okay, so I visually kind of put like a vertical line here. You wouldn't write that, but basically it's saying, what does x plus 5 look like only to the left of that line? Does that make sense? So what I always do is I say, I'm going to take that value and I'm going to plug it in right here. So if I do that, it gives me 4, right? Absolute value of 4 is 4. So at negative 1, I'm going to have a height of 4. So I'm going to put an open dot there because it's just less than, right? It's not equality. And I can keep doing so. So now x is now going to the left, negative 2, negative 3, negative 4. What that's going to do is it's going to graph that there. Does that make sense? To the left of negative 5, it's going to bounce back up. If we know what absolute value of x looks like this, right? The plus 5 is a translation, 5 units left, right? And that's what we're getting. Now the bottom rule, this here, says for x being bigger than 2. So now I've got kind of an image that I'm just thinking about things that are bigger than 2 now. The rule that I plug in is right there. So if x is equal to 2, excuse me, puberty, then the y value is negative 1, right? If it's greater than 2, so if it's 3, what's the y value? Negative 1. And that would be my final graph. So this portion over here, that is telling you what your inputs are, your domains. And then depending on which ones you're using, like I would use 3, that says because it's in that domain, you plug it in to that rule that it's aligned with.